All right, hi everyone. So this week our topic is this recent paper came out of Cornell University, and the title is "Harnessing the Universal Geometry of Embeddings." Um, I think this is um, a nice piece of work. It may not really change the direction of research, but in terms of understanding and interpretability and just as a technical engineering achievement, I think these guys did a really good job. So I'll start by reading a little from the abstract, and we'll kind of go through the paper. So it starts with, we introduced the first method for translating text embeddings from one vector space to another without any paired data, encoders, or predefined sets of matches. Our unsupervised approach translates any embedding to and from a universal latent representation. So we're not going to go deep into the background, but there are other people who've tried to do things. So you can take like two different BERT models. So let's say that you have like an original BERT and you have like a new Roberta model, and maybe you embed single words, orange, tree, computer, or maybe you embed sentences. Um, you know, Bob ate an apple. Okay. Um, and you do it in both models and you see what are the vectors that you get. And so if you do this on, whatever, a few thousand words, a few thousand sentences, then you can try and build a model that maps the embeddings from one model to the other. And people have not been very successful in doing this. And they haven't been successful even when they had sort of full access to both models, and you could like pick the sentence that you want to input into model one and the same sentence in model two. So you know that they're these paired, matched embeddings. People still have not been very successful in being able to map the embeddings from one model to another. So it's a little bit surprising that these guys were able to do this, and then we'll see that they actually not only mapped the embeddings from one text model to another, but they even did it even harder by saying that we're going to do this without actually having access to one of the models. So they say, amongst other things, our translations achieve high cosine similarity across model pairs with different architectures, parameter counts, and training data sets. I don't know exactly how different these are, but they had like 5 or 6 different models. And one of them was actually CLIP, so it wasn't even just exactly a BERT model. And one of them was not transformer based. And they got it to work pretty well pairwise between any one of these 5 or 6 different models. I don't find that the diagrams in this paper are all super helpful. So if you notice me skipping past them, it's because we might at some point go back to them, but they're not super helpful. All right, so in the introduction, they say like, hey, text embeddings are powerful. I don't know how many of you guys have, where's my Zoom window? There it is. I don't know how many of you guys have played with different things, but like these days, if you're building a RAG system, you probably have text embeddings for each document or document chunk that you're storing. You can now do things like sentiment using more of like a GPT style model, but historically a lot of stuff has been done with embeddings for things like positive, negative sentiment. There's still a lot of stuff that happens, a lot of similarity search. So the work that I do with security videos, when people want to do some, all right, so I was saying, with security videos, if you want to be able to do a semantic search on them, so all the videos where you see the guy in the blue jacket and the red ball cap, okay, that's all done by indexing the videos and doing embeddings. Though they're not text embeddings, in this case they're image embeddings, but still, so there's just a lot of domains where people store embeddings and do approximate nearest neighbor searches and other kinds of things. So they're still really, really common. And they say that an embedding of a text encodes its semantics. A good model maps text with similar semantics to vectors close to each other in the embedding space. I mean, technically speaking, you don't have to have a semantic embedding space, but I think the assumption is that all of our embedding spaces are semantic. So you would expect that things that are similar are going to be close to each other. It's not technically required of an embedding. So in practice, what we see is that different models, so if you're using whatever Roberta base, if you're using distilled BERT, whatever, each model encodes text into completely different and incompatible vector spaces. Whether the dimensionalities are the same or not, they don't.
Hey, Ted.
So, yeah.
Is it reasonable to assume that even given the same model, trained a second time, that the embedding space is completely different?
I believe people have tested, and the assumption is that it's likely to be some symmetry, like rotation and reflection and whatever.
Oh, okay.
But even with that, I don't think people have been able to demonstrate the veracity of that, because like let's say you have a 512 dimensional embedding, right? You could have a 10-dimensional subspace that's equivalent to these 10 dimensions over there, and it's rotated. And then you could have this other 4 here that maps to those 4, and it's reflected, and so on and so forth. So like you still need a very complex mapping, even if you assume this mapping is orthogonal. Yeah. There's still so many degrees of freedom. So
well, you talked about like even when you have a high degree of sparsity, that you get the space occupied by separate non-overlapping concepts in the same kind of dimension.
Yes.
So every one of those assignments, I would assume, would be pretty random.
Yeah. So maybe you can't even at that point, do it. Yeah. It's hard. So then they go on to define. There is a thing called the Platonic representation hypothesis. And this conjectures that all image models of sufficient size converge to the same latent representation plus symmetries, whatever. Okay. So, the simple thing that I go to is that the idea of the primary colors, red, blue, and green, has some relationship, and that maybe green is somewhere between blue and yellow in some way, shape, or form, right? And that all of these models have that same thing where green lies between blue and yellow in some way, okay? And so that's the hypothesis. We don't know if this is true or not, but the hypothesis is that.
Hey, Ted, they're not implying they're interchangeable, are they?
So
that these embeddings are interchangeable.
So ultimately, the strong Platonic representation hypothesis is going to say they're interchangeable if you just had a translator. And what this paper does is it builds translators.
Interesting.
Okay. So you could argue, and again, this is not going to be perfect, right? But you could argue that like English and Japanese are both languages, and they represent similar concepts, and you could build a translator that every English sentence maps to a Japanese sentence, and every Japanese sentence maps to an English sentence. There's still perhaps some nuance and stuff, and so it will not be a 100% perfect lossless translator, but I don't think anybody would be freaked out if you said, I built an English to Japanese translator. Okay. Prior to this paper, people would be highly surprised if you said, I built a Roberta to Distilbert translator. Like, here's these 2 Hugging Face models. You can download them, and I built a thing that will translate from one to the other. So if you give me a paragraph and I stick it into Roberta, and you take that paragraph and distill it into Distilbert, I can predict what your embedding will be without actually ever downloading Distilbert because I have my translator. So that's the idea behind this paper, which is pretty darn cool.
Yeah.
Okay. So they go on to say the universal latent structure of text representations can be learned and furthermore harnessed to translate representations from one space to another without any paired data or encoders. So what they're saying by paired data is where you pass the same sentence into both models. Okay, so they're saying nope, we're not gonna use that. All right. They're also going to say you could have your own private version of Distilbert that you trained, and I don't even need to have access to your model. But I do need something, and so what I do need is a bunch of data that you've made embeddings using your model. Okay, but here's the crazy thing. You don't even have to tell me what text you embedded. You just have to have enough volume of text that you've embedded with your model that I will be able to find the patterns.
Wow.
So they actually made the problem really hard on themselves. But an interesting thing is by making the problem harder, they might have seen through to the core principles of what it is, where the signal is telling them if they have a good translator or not. And so we'll see what it is that they did, but as a sneak preview. So one of the things they said is if you translate from English to Japanese and from Japanese back to English, then you should wind up with a sentence that's pretty close to what you already started with. And so whether or not you know whether the Japanese was good, at least you can say that my translator has certain strengths if I can do a round trip and I get back something pretty similar to what I started with. And I don't know, but I think, you could probably, if that was the only rule that you enforced, you could have a really terrible Japanese translation, right? Like hypothetically, you could have both be the identity function. So you say, my English translation of, Bob ate an apple is Bob ate an apple, and that's terrible Japanese, but it translates right to English back really, really well. Okay, so you do need some other properties other than just that cycle, but that was one of the things that they ended up doing. All right, so to continue going, and again, I'm skipping the diagrams on purpose because they're actually not. They didn't help me. All right, so what they're going to do is they're going to say, given unpaired examples of embeddings from the two models with different architectures and training data, our method learns a latent representation in which the embeddings are almost identical. So it turns out that for my toy example of translating English to Japanese, they don't do that. They say, I'm going to translate English to universal ease, and I'm going to translate universal ease to Japanese, and back and forth, but I'm going to have something in the middle that's universal ease, and I'm not just going to do a direct translation between the two languages. Okay? And the crazy thing here is this first part, given unpaired examples. So they will not have the same word or sentence embedded by both models. They will, and in fact, this is one of the things I had to go back and reread to make sure. When they train their model, they strictly ensure that the text going into each of they do actually have access to the model for the purpose of conducting their experiments, but they pretend they didn't have access to it, okay? And so in doing so, they ensure that the embedding strings for model 1 are 100% disjoint, and there is zero string commonality between the set of embeddings for model 1 and the set of embeddings for model 2 that they're going to build the translator on. So if the sentence Bob ate an apple appears in the embeddings for model 1, they ensure that that sentence never appears in the embeddings for model 2. So you can't even say, well, by luck, they might have a certain amount of overlap. They enforce zero overlap. So again, given unpaired examples with no overlap, our method learns a latent representation which the embeddings are almost identical. So this is, I'm using the analogy of they find a universal ease that they're going to translate everything to. So how do they do this? So they're going to use adversarial losses and cycle consistency. All right. So the adversarial loss, if you remember GANs, they're going to build discriminators that basically can say like, hey, is this an original embedding or a translated embedding? All right. And so if imagine that if your yes. So how do they do this? Adversarial losses and cycle consistency. So if you remember GANs, so they're going to build some discriminators. And so super simplistically, let's say the actual embedding is length 512 and you get a very dense vector. But as you build this translator, it's a little bit weak and it's doing something simple. And so we're going to have some discriminators. And if you had a translator that was doing something weak, and let's just say it wasn't really using the full dimensionality of the space, and a bunch of those 512 dimensions were all zeros. Okay, well, discriminator can immediately look and say, well, I can make a prediction that this is a translated embedding because I see all these zeros, and the real ones always have non-zero numbers everywhere, right? So that would be like an uber simple example of a way in which a discriminator could quickly tell them apart. And so this adversarial loss is pushing the translator to make its translated embeddings look realistic, okay? But realistic doesn't mean they're right, it just means it's realistic. So it's the other losses combined with if it has to be realistic, right? So if I have to translate English to an accurate Japanese sentence, that's one thing, but that doesn't mean it's the sentence that corresponds to the meaning of my English sentence. So if I have one loss that says all translations must be realistic grammatical Japanese, I've already accomplished a lot. Then the other losses are going to push to say, but is this actually correct, the right semantic Japanese? So that's the combination of tricks that they're going to use.
Is there some assumption about like the data that is embedded? It's not pairwise matching, but it seems like the concepts have to be similar in both of the language models, at least.
Yes. I think there is some assumption that you have to have sort of somewhat realistic coverage of the language.
Right. And the concepts.
So if you had one model that was trained only on Python code and the other was trained on plain English, then I don't think this will work because the Python code is such a tiny subset, you know. So I think they did say that at the beginning somewhere, but I might have skipped past it. But basically, they do require it. Maybe it's at the beginning of at the beginning of the next section. But yes, so they're saying that in this case they only test it where it's same modality, it's text. Okay, they think that stuff can be done with images or clip or other stuff, but like for starters, they just did text models and English. They're all English, and they were, we'll see in a second, the data set they were trained on has kind of a broad coverage. But yes, if I don't know what's a good example.
So like
super narrow.
If one was trained only on physics papers and another was trained only on literature, I can imagine that you just have no way of.
And that might still work because there's enough English language in those papers. I was trying to think of an example that's like even narrower than that. Yeah. Like error messages or something like that. You know, you might never really have a lot of grammatical things, and certain words might tend to
Right.
be highly omitted, you know?
Yeah.
So it is going to require that you have some kind of decent coverage of, you know. Here's a good one. If you just had like Dr. Seuss and other like children's books, then you're going to be missing a lot of more complex
Right.
concepts.
Right.
So my guess is that that would cause some problems. But this technique seemed to work pretty well, as we'll see later on. Um, okay. So we use a basic adversarial approach with vector space preservation to learn a mapping from an unknown embedding distribution to a known one. So what they're saying is we're going to start with model one, which is Roger's hidden model, and I don't know anything about the model. I just have a set of embeddings. So imagine that, like, Roger, you had a corpus, and you were using it for RAG. You embedded it all. You stored it in your vector database. Okay. Imagine that I stole a copy of your vector database, but I don't even know what the text is. I only know what your embeddings are. Okay. That's the unknown model. And then in order to build the translator, I do need a model that I have full access to that I can play around with.
Mm-hmm.
So that's the unknown one and the known one. So their claim is that their model that they call vec2vec is the first method to successfully translate embeddings from the space of one model to another without paired data. And they keep saying vector space. That's the conventional wisdom that these embeddings are living in a vector space where different directions mean different concepts. So to show that our translations preserve not only the relative geometry of the embeddings, but also the semantics of the underlying inputs, we extract information from them using zero-shot attribute inference and inversion without any knowledge of the model that produced the original embeddings. So what does that mouthful of words means? So zero-shot attribute inference is where I believe they're going to start with some medical text that they don't have knowledge of in advance, and they're going to ask their model to say, does this text contain diabetes? Does this text contain other particular attributes? Yes, no, kind of a thing. And then for the even harder problem, inversion, they'll say, here's an embedding, can you give me back the raw text that you think that this came from? So technically speaking, when I talked about English to Japanese translation and all that stuff, they're translating one embedding to the other embedding. They're not actually translating the text that the embedding came from to the text for the other embedding, if that makes sense. All right. Any questions before that was kind of the overview, and obviously we haven't explained really how they're going to do this, but now we're going to get into it. Any questions before we dive into the actual technique?
A quick question. If I have a model that I do have full access to, and I get produce embedding for a text, in that case, am I generally able to generate the text that from the embedding? Is that a common
That's
understanding?
actually non-trivial in and of itself. So just
Okay.
inverting and embedding back to the original text is not super easy. If you remember the what was that meta paper called? There are these two papers that came out. There's the byte level one, and then there was the other one that was like big semantic chunks. I forget what they called it. Large concept model. So LCM, they used some previously trained model that would encode phrases and also could unencode phrases into plain text English. And they purposefully did it because it's not super easy, so they would rather just reuse that model than have to train their own from scratch.
Okay.
All right, so here's how they formulated the problem. So consider that you have a collection of embedding vectors, and they're going to call these vectors from the unknown model, the one hypothetically you could say that you're attacking this model, whatever you're trying to decode. So you have little n embedding vectors, and they're just U1, U2, U3, U4. You just have a pile of these. And so the easiest example of this, the mental model would be, is if somehow you got to dump a copy of a compromised vector database. So you don't have any of the text that was used to create these embeddings, but you still have a fairly large set of embeddings that represent a good amount of, we'll just use English. It doesn't have to be English, but we'll just say for simplicity, a good amount of the English language. Okay? And so you have a model, big M sub 1. That's the model that was used to create these embeddings. Okay? And so then you have your raw text, D sub I, and each D sub I gets turned into an embedding U sub I. Okay? But all we have are the U's. We no longer have the D's, and we don't have access to the model itself, M1. Okay? But in the formulation, we say there does exist a model M1, and there did exist the original text strings D1, D2, up through Dn, but we just don't have access to those. All we have access to are the embeddings U1 through UN. Okay? And so this is all from an unknown model, you know, BERT something or other, whatever, some model that we don't have access to, M1. And the formal definition here is that, you know, a vocabulary of a string of length S going into, you know, a bunch of floats where D sub M1 is just whatever the size of that embedding is. So we'll just use 512 as a round number. Okay. And then an unknown document D sub I. So in this formulation, we don't have model M1, so we cannot make queries to M1. We can't say, hey, what's the embedding for Bob ate an apple in model M1? Okay, we're just stuck with these embeddings, which are not necessarily embeddings we want. They're embeddings of just unknown text. And so they say, for the purpose of their problem formulation, they don't need to know anything. They don't need to know the architecture of M1. Is it a big model, small model? Is it transformers? How many layers? They don't need to know anything about its architecture. They don't need to know anything about its training set. They do need to, we'll see that this set of embeddings has to be a certain size. For their experiments, their main experiments, they had 1 million embeddings, okay? So this is not going to work if you only had 100. Okay, it's going to need a fairly large amount of data in order to have coverage of the English language. All right, so their goal is to extract information about, one way you can think about this is, one goal is to extract information about the documents DI. So once they build these translators, then they will be able to say stuff like, is diabetes mentioned in this document? Is airplanes mentioned in this document? And they might even be able to say something like, is George Washington mentioned? Is Brad Pitt mentioned? And things like that. Yeah, Dave, you have a question?
So when they say at least 1 million embeddings, that's essentially the tokens?
No, because remember, these are vector embeddings. So if you think of this as like a RAG database or a BERT type model, you're sending in sentences or paragraphs or even like document chunks, and they're just getting embedded into a a vector of, say, 512 floats, and that's what we have access to.
And how is that different from tokens? I'm just trying to understand. Like, of course, it
So
depends
these
on
are
the
mostly,
embedding.
just so you know, these are mostly BERT-based models, so it's not even a GPT style model, so we don't even think in terms of embeddings. We just think of how many string inputs there are.
Got it.
Okay?
Yep.
So Ted, when you're kind of setting up the kind of the scenario here, it kind of sounded like they were trying to explore, if I gained access to like a RAG database, could I somehow figure out what's in that RAG database?
Yes. Yes,
But
if they
then
had
you,
a perfect translator, they would actually, without access to your embedding model, they would be able to reverse engineer the full English text exactly of what's in there. And so, for example, if you had encoded in there a proprietary internal document about the company's plans for 2026, they would be able to, merely from having the RAG database, be able to read the clear text of your
okay.
2026 plans.
But then you said that it requires a kind of some minimum size, or at least a large amount of embeddings for this to work. Which, okay, I get that. But you also said that it had so that it has good coverage of the English language. So I'm wondering if I just have like my corporate documents that, talk about corporate things, right? But doesn't cover all the breadth of subjects that exist out there in the English language. Would 1 million embeddings of my corporate documents be sufficient? Or do I have to have the full breadth in the embeddings that I wish to decode?
I think it would probably work.
Does that make
Um,
sense?
yeah, I think it would probably work. We'll see, and I'm not 100% sure. I'm not
Okay.
right, one of the authors of the paper, but um, um, again, it couldn't be 1 million Dr. Seuss sentences. Uh,
Yeah.
but I think there is still enough variety of sentence structure in 1 million corporate documents,
Hmm.
right? It doesn't need to like use every single word in the English language, right? The patterns they're going to look for are things around nouns, verbs, singular, plural. I think a lot of those are the more basic concepts that they're going to learn. And
Okay.
so those are going to be present in everything. But you just
Okay.
can't have like baby talk and expect it to work.
Okay.
If all the sentences are C spot run, then I don't think it would work. But
Okay.
as
So
long
you're
as the
thinking,
people in your business documents are writing complete sentences and making arguments and stuff, my guess is it'll work. It won't work as well as if you had even broader coverage, right? You know, but it'll work.
right, right. Okay. So you think it's mostly picking up, or at least initially picking up on kind of language structure
Yeah,
aspects.
yeah.
And maybe some of this, maybe it doesn't know that pronoun and it's going to get that wrong, but it understands it understands
Hmm.
structure that pronouns in.
Yeah, yeah. And hopefully you guys can kind of
Okay. That
dig
makes
in
sense.
if you're curious and see for yourself whether you think it can get further. Um, yeah, okay. So that's the sort of unknown system, the side that you can think about. What if we were attacking this? Okay. They do assume that you have access to your own encoder M2. Okay, and that's a very reasonable assumption because anybody can just go to Hugging Face and download some version of, Roberta or whatever. Okay, and for this, you have the ability to pass in whatever strings you want. So needing 1 million of this is not really much of a barrier because anybody can go, and just embed a bunch of different strings or paragraphs or whatever. Okay. Um, So here's the sentence that I was looking for before. We assume high-level distributional knowledge about the hidden documents under Model 1, so like the modality that they're text and the language that they're English. Okay, so they're not saying you really need to know these are corporate documents or these are scientific papers or whatever, but they do barely say it has to be English text, for example. Okay, to extract information, we may translate all of these embeddings used from the hidden model into the output space, the embeddings of our new model M2, and apply techniques like inversion in order to then say, if I have an embedding of M2, then let me invert it, let me reverse it, and get the raw plain text. So, not going to go into a lot of detail, but they say there's been other prior research of the problem of matching or correspondence between sets of embedding vectors. And these typically assume that the strings for the two encoders have identical or highly overlapping inputs. So even people who've studied where they take 100,000 strings and they embed it with two different models, and you know that they're all paired, trying to build something that just exactly matches the right pairs of embeddings has proved difficult. And I'm not going to talk too much about, and I don't necessarily know all the references, all the prior art in terms of trying to do this. I just do know that it is hard and nobody's claimed that they're super successful. They say there's a little bit of work translating between embedding spaces without overlapping inputs, and they claim in our experiments, these prior methods that tried to do non-overlapping inputs all struggled significantly, and we kicked their butt. We did a great job. That's basically, that's what you have to say in a research paper, right? Is we did so much better. So their task is inherently much more challenging than matching because you don't have corresponding input strings. And in fact, again, like I said, they ensured that there is not even one single string that's identical between the two different models, between what got embedded with the different models, okay? So they don't assume that they have access to the first model, and they don't assume that the documents, that they have access to the documents, or that if you had access to these documents, then you could also embed them yourself. So I'm just gonna mute here. Yeah, thank you. Dave, another question?
Yeah, so I mean, in some sense, it looks similar to, you know, the translation, not the translation, the text to speech, where you, or speech to text, where you have someone read the text, but you don't know the embedding for that, and you don't have the embedding for your audio, and then you still get the perfect model for text to speech or speech to text. I mean, that's what I think Meta did some time ago, right? 2 years ago. So Vec to Wave to Vec to or something like that.
Yeah, I think it's even harder than that, but you do raise a good point. So if you know that this one sentence has 10 words and somebody spoke it and it took them 10 seconds just for round numbers, okay? You really don't know word one. Did it start at the beginning and last 1 second? Did it start at the beginning and last a half second? Did it start at the beginning and last 2 seconds? And that's for the first word. By the time you get to the middle of the sentence, you have so many unknowns, you don't know where it started or where it ended, and it's very difficult to do that. But you do still have, at least going for you, that that the sounds do correspond to that same set of words, okay? In this case, basically what they're saying is, I'm going to give you 1,000,000 English sentences and 1,000,000 Japanese sentences, none of which are pairwise ever saying the same thing. And from that alone, I'm going to build a good English to Japanese, Japanese to English translator, which is freaking crazy because you don't actually have pairs.
Right. Thanks. Yeah.
Yeah. So the problem is actually like a lot harder in that sense. Okay. So they say we rely solely on unsupervised translation from M1 to M2, and this requires, it depends on identifying and leveraging shared geometric structures within the embedding spaces produced by M1 and M2. So that's why the title is Harnessing the Universal Geometry. If models M1 and M2 just had figured out some completely different geometry for representing their data, you wouldn't be able to solve this super hard problem. You know? If model M1 was somehow figuring out ways to build little circles and represent, words and concepts based on rotations of these little circles. And model 2 is doing something completely different, where it's I don't know, building multi-dimensional hexagons and da 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 da. Then they wouldn't necessarily be able to from unpaired sentences, right? But what they're saying is, hey, it doesn't matter. Yeah, and again, I don't know what these geometric concepts are, but you have subjects of sentences, and you have action verbs, and you have objects of sentences, and you have singular and plural, and many and few, and somehow these things, when you have enough examples, in order to line these two things up, the best way to line them up actually works out pretty decently.
Did they define, or do you have a sense or understanding of what a geometric structure is in a knowledge model or in an embedding space?
So the way I think about it is like the color wheel example that I gave before, that like red, blue, and yellow are the primary colors, and green, orange, and whatever purple are like in between them, and verbs are things, and nouns are things, and that whatever, big and small may be somewhat related to singular and plural, but not exactly, you know what I mean? And that these kinds of relationships ultimately end up having similar representations. When you are challenged with the idea of taking a language that has so many concepts and squeezing it into something small like 200, 500, 1,000 dimensions. So they're all challenged with this. And so they're going to have to say, these are the couple hundred most important, most frequent concepts that I need to capture in order to minimize my loss, and that they're going to have somehow similar geometries. In terms of some things may be orthogonal, right? So like color may be orthogonal to count. And so that's not a terribly usable relationship, but it is one that you can then enforce to say that you can't accidentally map red from one model to 3 in the other model, because it doesn't work well, right? So I don't know. They don't actually talk about what they are. They just say that we posit that there must be these things. Okay. And so, in fact, the next paragraph is about this strong Platonic representation hypothesis. So they say, we hope that this unsupervised embedding translation is possible. And this is, again, unsupervised, meaning that they don't have pairs, matching pairs, okay? And the stronger version of the Platonic representation hypothesis, our conjecture is as follows. Neural networks trained with the same objective and modality, so text, for BERT, it's kind of this mass language modeling, predict the missing word, right? But with different data and different model architectures, are still going to converge to a universal latent space, such that a translation between their respective representations can be learned without any pairwise correspondence being provided to build the translator. All right, so then they further say that if we can build translation, then this enables information extraction. So if you solve the translation problem, this will allow us to use information extraction tools designed to operate on vectors produced by known encoders. So I thought this was like a really cool paper, just because it's like engineering wise, it's really cool, and they did a good result. If you're more interested in information security, what this says is, if you care about the contents of your RAG database, okay, if it's not public facing, okay, then you better secure this, because just because they don't have access to the plain text does not mean that they can't access the plain text that these guys are saying that they say that theirs is not perfect. It clearly wouldn't be, but if this is the lower bound on what's possible by an attacker, then you should worry. You should make sure you secure. If the documents like my company has in a RAG database are all for the chatbot for our public website, then you don't have to worry about securing it because you're actually feeding all that information to your public website anyway, right? But if you had some, like, say, internal to my company chatbot that is not supposed to be used by people outside the company, then one of the implications of this is one should guard the vector database roughly, not exactly, but roughly as securely as you would have guarded the plain text documents that were used to create that vector database. All right, so let's talk about the method. The method gets a little bit gnarly, and we're more than halfway into the meetup, so let's see if we can get through this. So they're going to propose a modular architecture. It's going to turn out to be made of lots of little parts, and so it can get a little bit confusing keeping track of all little parts. So the embeddings are encoded and decoding using space-specific adapter modules and pass through a shared backbone network. We'll see what that means. You don't have to fully understand this. So they're going to have input adapters, and the input adapters are going to be named A. So for model 1, the adapter is called A1, and for model 2, the adapter is called A2. And these guys here are going to all map from whatever their embedding dimension is, D, okay? They're going to map to our universalese in between dimension Z, okay? So we're going to pick some arbitrary Z that we think is big enough for our universal thing, okay? And so again, so you have a vector embedding, and A is going to turn that from model 1's embedding. It's going to turn it into my universalese embedding of dimension Z, okay? This one took me a little while to sort of understand. There is this shared backbone T, which takes an input from our Z-dimensional space and just outputs another thing from the same Z-dimensional space. And I'm not 100% sure, but I think that basically what this does is it T ends up finding the minimum necessary information in your latent space that's Z-dimensional, but Z can be higher than the minimum necessary. Okay, so if you had like numbers modulo 12, you can essentially think of them as like the points on a clock. Okay, and so a good representation of this is just to have them in a circle. If I embedded numbers modulo 12 into a 8-dimensional space, the reality is I only need 2 of the 8. The other, I have 6 degrees of freedom for how to orient the circle in my 8-dimensional space. That doesn't matter. Okay? And so the way I think, and this is not written anywhere, but this is my interpretation of the paper, is that what T would do is it would ultimately extract only 2 dimensions out of the 8. All right? So my thinking is that if all you needed was to represent the 12 numbers modulo 12, then T would input something that's full 8-dimensional, and it would give you an output that's 8-dimensional, but it would only be rank 2. All right, so it's getting the core. If you didn't have this T in there, then you'd have to pick the exact right number for Z. But by having this T in there, what I think it allows them to do is to say, well, let's just err on the side of I'll do 512 or I'll do 1,000. That should be big enough. And then if it's too big and there's all these extra degrees of freedom, then T is basically the thing that says, but let me simplify and just get actually the part that's truly necessary. So what we're going to see, we use T, but we don't ever use T inverse, so to speak. But for everything else, we have forward and backward functions. But T is the only one that we only use once. And so I think that's because it's saying T, in my mind, they don't use these words. T is doing a down projection, and there's never an up projection because as long as you've retained all core meaning, you don't ever need to project back up. You just stay in your minimum necessary size space. So that's my guess what T does. All right. So the adapters A go from model-specific embeddings to universal embeddings. The B's go in the reverse direction. Those are output adapters that go from universal embeddings back to model-specific embeddings. Okay, so they go from z-dimensional to d-dimensional. So now, if I were to write a translation function that's going to translate from a Model 1 embedding to a Model 2 embedding, okay, so F1 is going to translate from Model 1 to Model 2, then what that's going to be is B2 compose T compose A1. So in other words, I'm going to run A1 on my Model 1 embeddings to convert it to universalese. I'm going to project it down using T, and then I'm going to convert it to Model 2 using my reverse mapper B2. And then you swap the indexes to convert from Model 2 to Model 1. Then it's A2 compose, well, whatever, depending on your read right to left. A2 and then run T and then run B1. Okay. I can also do reconstruction mappings that just go in a circle. So I can go from Model 1's embeddings to universal embeddings, down project, and then go right back to Model 1. And in theory, I should wind up with the exact same thing that I started with. And then you can do the same thing for Model 2. I can go from Model 2 embeddings to universal and back to Model 2. So this is 4 functions you can have. F1 and F2, and reconstruction 1 and reconstruction 2. Does that make sense?
Mm-hmm.
All right. So the parameters that we're trying to learn to build vec-to-vec are the parameters for our forward adapters, A1 and A2, our shared backbone, as they call it, I think of it as the down projector T, and our reverse projectors B1 and B2. And if we can learn really good parameters for these, then the way you translate from one model to another is you actually need to compose 3 of these things in a row. You can't just use one at a time.
All right, sorry, I think my computer may be overheating. We had a blackout a little while ago, and my power supply got fried, and I think my computer hasn't been the same. Maybe it actually kind of got fried too. All right, so we currently have these 5 models that we're going to build, A1, A2, that translate from embeddings to our universal thing, this T, and then the reverse translators back from universal to individual models, and then the parameters for these neural networks. When you combine them all, this is the complete set of parameters theta that we're trying to learn, and that makes up vec-to-vec. That makes up our translator. All right. However, in addition to these completely necessary components, we're going to have additional models that we're going to train. We're going to have discriminators that we build, and this notation confused me at first because this looked to me like f of, but actually no, this f and these parentheses have nothing to do with each other, so it's just a list. So we're going to build 4 discriminators. We're going to name them D super L for latent, okay? But we're going to have latent 1 discriminator, latent 2 discriminator, and embedding 1 discriminator and embedding 2 discriminator, all right? And so this is what I mentioned before, where basically they're going to say, for the outputs of these models, we're going to try to discriminate native embeddings from ones that were translated. Okay, and so this we're going to see there's going to be an adversarial loss where we're saying the discriminators are going to try to tell real from fake. Fake not being like, bad, but fake. Okay, and then ultimately, here's this expression in equation 1, which is this you're trying to maximize the discriminators, you're trying to minimize the loss from the parameters, and then here's a detail on all the different loss components. Okay, so for the adversarial loss, we're just simply going to have the losses of the 4 discriminators individually all summed together. Okay, so a discriminator that can tell the difference between original outputs from the outputs of F1, a discriminator that can tell the original outputs from the outputs of F2, and then we're going to have a discriminator that can tell the difference between T compose A1 and original embeddings and T compose A2 from original embeddings. So that's the adversarial loss component. Now the next part, so again, if we just had the adversarial loss, that's going to say, are we mapping to valid embeddings? So that's like, am I mapping from English to a valid Japanese sentence? But it doesn't mean that it's a Japanese sentence that has the same meaning as the English sentence. All right? So that's what they mean by adversarial losses don't guarantee preserving semantics. So we're going to have 3 additional losses here. Okay? The first is the reconstruction loss. And so basically that's going to say, so when you do images, you usually just do like L2 loss on the pixels. Okay. So in this case, we have embedding vectors. We're going to call them X. Okay. And so we're going to do L2 loss on our embedding vectors. So model M1 is a Roberta model that Roger has that I don't have access to it. But here's a vector X. I'm going to translate it to universal and then translate it back to model 1. And I'm just going to measure the L2 distance to see if it got back close to where it started. And I'm going to do the same thing with model 2. So that's reconstruction loss. Cycle consistency is we're going to go farther now. We're going to go from model 1 all the way to model 2 embedding, and then from model 2 embedding all the way back to model 1. So technically it's a superset of what we did for reconstruction loss, except now instead of just going to universal, we're going to keep going from universal to the other models, and then we're going to go back to universal and then back to whatever. So this is an even bigger circle than just reconstruction. And so we're going to have a loss, again, just L2 loss on the floating point values of our, say, length 512 vector. And then this one I think is important. They call this one the vector space preservation loss. And so they're going to calculate this batch-wise just because it's impractical to do it across the data set. So they do it only for each batch. And so what they want is that the pairwise relationships between generated embeddings remain consistent under translation. Okay? So it says here, given a batch of embeddings, embedding X's and embedding Y's, we're going to sum their average pairwise distances after translation by both the model 1 translator and the model 2 translator.
What's the distance function?
What was that, Roger?
I'm just wondering, what's the distance function they're talking about?
Again, you can just see it's just L2 norms here
Just an
being
L2 norm.
used. Okay. And an oversimplification of this, okay, is that if you have 2 different embeddings, I and J, okay, and they mean completely different things, and you dot them together, you should get a 0 result over here. And so then you want to get a 0 result when you translate them. Okay, so if 2 concepts are completely orthogonal, they should be orthogonal after translating. If 2 concepts are non-orthogonal, they have a very high similarity. So if you have Bob ate an apple and Bob ate a red apple, and they're both very similar before, then you would hope that they stay very similar later, and not only that, they're actually enforcing not only that they, well, these are not normalized dot products. So not only are you want them both to be non-zero, but if this one's a 2, you want this one also to be a 2. So not only are we preserving orthogonal things should stay orthogonal and non-orthogonal things should stay non-orthogonal, but we're actually saying that distance should be being preserved across translations. And so that, a dot product of 4 should mean the same thing before and after. So that's kind of crazy, if you ask me.
So those are dot products of the M1, M1, and F1, F1, right?
So M1, so embedding string I, embedding string J, and then translating the embedding of string I and translating the string J.
But,
so basically, if
but
you
is
start
that
with,
operator that is the dot just a dot operator? Dot matrix multiply?
yeah, this is just
The
a
dot product
regular.
of two vector embeddings?
Sorry, your audio's breaking up a little bit,
Dot
but this is
product
just
of
a
two
regular
embeddings.
dot product. So the embeddings are one-dimensional, and so this is just going to be embedding I transpose matrix multiplied with embedding J, a regular dot product, which is going to give you a scalar. It's going to give you
Yeah, okay, that's what I was wondering.
a real number. Yep. So this vector space preservation one, I think, is one of the most important losses. So all these other ones are trying to get it not to do mode collapse, trying to get it to do good things. But I think this is the one, when they talk about universal geometry, this VSP loss is the key one that says concepts that have a certain distance from each other. So this doesn't say in what direction the distance is. Okay? It just says a certain distance from each other, so to speak, in terms of cosine similarity. But the thing is, if every single pair of embeddings has the right distance from each other, that ultimately means that they have to actually be in the exact right place, right? So if you had a map of the United States with different cities and you knew the exact distance between every pair of cities, like traveling by highway, I think there's more or less only one way you can plop the cities down on the United States in order to have those sets of distances. And then symmetries. So if you just took a mirror image of the United States, then you would end up with the same thing, but Florida's on the left instead of on the right, right? But you can't have all those distances without actually having everything in the exact right place. So that's what I think this loss. This is the really key loss here. All right. So I did go through that a little bit fast in terms of here's the min-max GAN like formulation. Here are the 4 GAN losses, and here are the 3 whatever you want to call losses related to our translators that we're building. Okay. I think I'll pause here for questions and we might end up stopping. Then what it gets into is they talk a little bit about what was the data they used to train it, and then they're going to show the results. The results are going to be good, but if we do want to go another week, then we will see not just that some of the numbers are good, but they have some specific examples. So they say, like, the model was trained on like Wikipedia-like questions, and then we passed it in letters from the Enron trial, and it was able to do certain inverting where they actually pulled out small strings that you would not necessarily expect it to be able to know. And the one that I thought was really cool was the word Enron is not in the vocabularies. And this one thing was able to invert the letter N and then RON, Ron, like the name. And it was just trained on Wikipedia, but somehow it was able to invert N, Ron. from just looking at an embedding of sentences. It wasn't like even a single word embedding. It was just, sentences or paragraphs or whatever, which is a pretty wild result. So any questions about these losses?
Kind of, yeah, you kind of answered my question where I thought that it will be able to map only the embeddings for words that appear in both the corpus, but I think it is able to do more than that because, like, in some languages, genders are not there, for example, right? Or pronouns or words, maybe complex words. So, but what you said is it is able to somehow do that from the vocabulary.
Yeah, and they had 1,000,000 sentences, remember? So, or paragraphs, I'm not even exactly sure. But so, they do have pretty broad coverage in this. And you can say, like, maybe it wouldn't have been quite as good if they didn't have as much. But again, that you could somehow start with 1,000,000 sentences encoded by Model 1 and a different 1,000,000 sentences with none in common encoded by Model 2 and actually build a translator. So I thought that one of the nicest things about this paper was just figuring out that this problem might be impossible, but if they share a geometry, then these things like being able to circle, go from Model 1 to Universal and then back, or Model 1 to Model 2 and then back, that these are sort of like universal things that it should be able to do. And just by combining all these losses and then having to tweak what is the relative strength of each of these losses, how much do we weigh them, right? So I thought that was, just from an engineering perspective, pretty cool. And GANs, I do not think will ever be in a leadership position in terms of actually being used to generate images. But the lessons learned from adversarial losses that we got from GANs, I think will stay with machine learning for a long, long time. And I think these adversarial losses were probably quite helpful in this case. Because again, what this adversarial simply says is that when you translated it from English to Japanese, you got a valid Japanese sentence. It doesn't mean you got the right sentence, but that alone is doing a lot. Just simply saying, is this a valid looking, realistic looking end result? Yeah, Terry, you have your hand raised.
Yeah. I have a question about the GAN loss in the latent space, the second line of the formula. So it's the discriminator is discriminating the T compose A1 against what? What is trying to discriminate from? For the first line, it's a bit easier to understand. It's just trying to discriminate the F1 against the true input. But the latent space one, because it's the output of T compose A1 is in the latent space. So what's the true?
Right, we have all of our latents come from composing T with either A1 or A2. We have code.
Where was the D1 and D1L defined? Were those up above?
It's very skimpy. It's just right here. It says we introduce operators. So it's clear that DL is looking at a z-dimensional vector. And so if you translate from Model 1 to Model 2, you have regular Model 2 embeddings to compare them to. But if you translate Model 1 to latent, we don't have anything to compare them to. So what is it discriminating? That's a really good question.
Is this something we can answer
what-
today, or maybe sounds like we're coming back next week anyway.
Yeah.
Yeah. That's a really good question. I will have to try to see if I can understand, or I'll look at the code for this particular loss, because when you translate from Model 1 to Model 2, you can compare your translations against just regular Model 2 embeddings to see the Model 2 embeddings are real and the translations are fake, and you're trying to see if you can discriminate real from fake. But in this case, we don't have. I don't know what the real is that you're comparing the translations to. That's a great question. Yep.
Yeah. Yeah.
Good one. You stumped me,
All right.
Terry. No, it's actually a really good question. I'm glad you asked.
Thank you. Thank you. I will try to read the code. Try to understand.
Yeah.
Dave, you had another question?
Yeah, I just wanted to know, like, given that the actual loss that kind of, that M1 dot product, M2, and then translated values dot product. So in the end, it will try to get the mapping for each token or each embedded vector. Basically it was just all over because, it doesn't match with anything on the other side eventually. From one language to the other.
So I heard what you're saying, but I'm not quite sure I heard the question. What's the question?
So were there some embeddings that didn't get mapped from the other side?
So like when you build a dog versus cat classifier, in theory, you can get to zero loss if you have perfect classification. In this case, they'll never get to zero loss because I think that's what you're getting at. Because the embeddings are not paired, so there is no exact opposite in M2 to match a given embedding from M1 to. So if you're just doing a circle from M1 to universal and back, you could get a zero loss. If you do a circle from M1 to M2 and then back, you could get a zero loss, because once we go to M2, we're not mapping it to the nearest M2 known embedding. We're just mapping it back, and we're doing the same thing with M2 embeddings. So then the really interesting one is this last one, the VSP one, where they say that the distance between any pair of embeddings from Model 1 should be the same as the I'm using the word distance even though it's a dot product. It's, cosine. It should be the same as the distance in universal space of the translations. And the same thing has to be true from Model 2 to universal. Therefore, what we actually expect then is that, and the round trip thing. By virtue of that, basically you're aligning both Model 1 and Model 2 to the same universal. In theory, I was thinking about this. I don't think they tried this. But you should, once you've got a universal that you used between two pairs of embeddings, you should figure out a way to be able to reuse that universal for different things and say, well, maybe I train a new T, but in theory, you should be able to reuse that same thing. And I didn't see them address that in this paper, but I think that would be a fairly obvious thing to do. If you're claiming that it's so universal, then you should be able to just sort of reuse it. But we'll get to it next week. But basically, what we'll see is that this is by no means a perfect translation. Okay, but they'll do things where they'll say like, hey, the embeddings in like M1 and M2 don't look really all that similar. You can see some of them have very small, close to zero, very blue looking cosine similarities. But then once we map them to universal, then all of a sudden they have very close to one. And I'm assuming this is averaged over tens, hundreds of thousands, millions of strings. They're saying that, in the two different things. So it's clearly a non-trivial task. The vectors did not start out aligned, but they ended up being pretty reasonably well aligned. And again, this is for the purpose of evaluation. Okay, the same pairs of strings were not available during training, but during evaluation, we do use the same strings to see how well it did, and some of this other stuff.
Yeah, thank you.
All right. So yeah, for purpose of time, I think we need to wrap up. But any other questions just about, again, there's a lot of components. There's A1, A2, T, B1, and B2. And then they nickname these compositions F1 and R1. But eventually they use these F1s and R1s in places like here when they're doing things like cycle consistency. Just shorten the notation. Otherwise, this would have been a triple function call, and that would have been a triple function call, and it would have just been very, very, very verbose. All right.
Well,
So we'll stop here. I don't know, Roger, Jerry, do you think that we plan the whole time for just continuing on next week, or do we want to try and see if we can squeeze in something
is Neha
else?
still, I see she hasn't signed out yet. I don't know if she's still able to talk.
Yeah, she's just unmuted. So,
Hi.
Jerry, you can end the recording.